In class, please don't call me sir. That's a nobility title in the UK. We don't use that here. So, inter-process communication. Do you have any questions about the about the first session before we continue? Sorry. Any questions about the first session? Okay. So, continuing with the example that we had, here we have a main method, which basically will create a child process, and the parent will basically send 5 times a certain message from one end of the pipe, and the child will read it and simply print it on screen. So what do we see? We see that an integer array of length 2 is declared in order to hold the file descriptors. The pipe is created using the pipe system call. With fork, we then create the child process. If the return value is 0, that means we're in the child process. We close the writing end of the pipe because the child is only interested in reading from the pipe. It uses fdopen in order to convert the file descriptor to a file stream. Now, this is of course not necessary. You can perfectly use a file descriptor as an integer, not necessarily a file pointer. But there are certain advantages to opening a file as a file pointer in order to benefit from the C library of input-output functions. And on the other hand, we have the parent process in the else clause, which simply asymmetrically closes the reading end of the pipe because it is only interested in writing to the pipe. It converts the file descriptor to a file pointer and then calls the writer function, just like the child calls the reader function. And what do these two functions do? Very simple. The writer function writes in a for loop the message count times, and it flushes it after F3, printf, then sleeps 1 second between iterations. Now, what does the reader do? The reader simply holds a buffer of 1 kilobyte, and as long as it hasn't reached the end of the stream, it continues reading from the pipe using fgets, so line by line, into the buffer, and whatever it reads, it prints it on screen to std-out, to standard output, using fputs. That's all there is to it. Any questions about this example? If you're not asking anything, I'm assuming that everything is clear. Okay, class? So we can use a pipe in order to communicate unidirectionally from a parent process to a child process. However, we have also seen that we can use the pipe implicitly by using the vertical bar symbol on the command line in order to connect the standard output of one command to the standard input of another command. The standard output of the command to the left of the pipe connected to the standard input of the command to the right of the pipe. Now, this part is important. When a pipe is created, the file descriptors used for the two ends of the pipe are the next lowest number descriptors available. So the file descriptors, as you know, they start from 0. So 0, 1, 2 are by default occupied because whenever a process starts executing, 0, 1, 2 are automatically opened by the kernel as the standard input, output, and of course, the standard error files. So that means when you call the pipe system call and you need 2 more file descriptors, it will use the next and lowest number descriptors available. So if 0, 1, and 2 are occupied, and if you haven't opened any other files, it will use which numbers? I'm just checking if anybody's listening. Apparently not. It will use, of course, 3 and 4. And of course, if they are not available, well, in that case, it will continue with 5, 6, etc., etc. So how can we bring about the situation where two programs that read from the standard input and write to standard output are connected using a pipe, since the pipe system call uses the next available file descriptors? So how can you connect the one file descriptor of one command to the zero file descriptor of the other command? And of course, the answer is by duplicating file descriptors. So how does it work? Well, the idea is very simple. Now, one way of doing this, one way of accomplishing this, is to, of course, first declare an integer array of length 2, call the pipe system call so that the pipe will be created in kernel memory as a buffer of maximum 64 kilobytes. Then you can have, well, let's say that this, of course, call will allocate some file descriptors, but of course not 0, 1, and 2, because they are already open for the file descriptors as standard input, output, and error. So let's say it occupies 3 and 4, or 5 and 6, or 10 and 11, who knows? Some other numbers other than 0, 1, and 2. Well, in that case, what you do is, first, you close the standard output. So close standard output file descriptor, which means file descriptor number 1 is now free. And then if you call dup, which is a system call for duplicating file descriptors, and if you duplicated the PFD1, so the writing end of the pipe, now dup will duplicate it. And of course, it will duplicate it using the next lowest free file descriptor. And in this case, since 0 is occupied and 1 is free, in that case, the copy of PFD1 will be 1. So the writing end of the pipe will have a copy as file descriptor 1. So file descriptor 1 and the file descriptor in PFD position 1 will both be pointing to the same file, which means whatever you write using printf or whatever you write to the stdout standard output file descriptor will go to the writing end of the pipe. And of course, you can act similarly in order to connect standard input to the reading end of a pipe. Any questions? Now, a tricky situation at this point is that dup assumes, the dup system call assumes that 0, 1, and 2 are already open. If, however, 0 was closed, so that means if 0 was available, well, in that case, the copy of PFD position 1 would become 0 instead of 1, since that is the first free available file descriptor. And that is why it is a better idea to use dup2 instead of dup, or rather instead of close and dup. Why? Because if you use the dup2 standard dup2 system call, you have the possibility, you have the opportunity to actually tell it exactly what or which file descriptor you want the source copied as in the target. So for instance, if you call dup2, you don't have to basically first close the target file descriptor because it will be closed in your place, but you tell it specifically to make a copy of PFD at position 1, a copy as standard output, so as file descriptor number 1. And it doesn't matter if file descriptor 0 is closed, if it is available, because with dup2, you tell it specifically, I want you to make a clone, a copy of PFD position 1 as standard output, so that both file descriptor 1 and PFD at position 1 point to the same file. That is why we don't use dup, we use dup2 in order to accomplish this goal. Now, of course, after calling PFD1, after duplicating PFD1 using, of course, dup2, that means you have two file descriptors pointing to the same end of the pipe. So you have two file descriptors pointing to the writing end of the pipe. Now, since you don't need two file descriptors for the writing end of the pipe, well, of course, you need to close one of them. And of course, you are going to close PFD1 since you have accomplished your goal and standard output is now pointing to the writing end of the pipe. So if we put all of this together, if we put all of this together, let's look at an example in source code of a pipe that is established between the commands ls and word count, So what do we do? First, of course, we declare the integer array of size 2. We call the pipe system call so that the pipe is established in kernel memory. So PFD0 contains the reading end of the pipe and PFD1 contains the writing end of the pipe. We call fork. So now we have two processes. We are checking if fork fails or not. Okay. If we are in case 0, that means this is the child code that is being executed. So what does it do? First, it closes the reading end. The child is closing the reading end. Okay. Now the child is duplicating. Now the child, by the way, is going to represent ls. So ls has nothing to read. That is why it is closing the reading end. It is only interested in printing its output to standard output, but it wants standard output to be connected to the writing end of the pipe. So what does it do? It first closes the reading end, PFD0. Now it must duplicate PFD1 as std out. It first checks with an if that is already in place for whatever reason. If that is not the case, well, in that case, we have to explicitly copy it and close it. So we call dup2 and we make a copy of PFD1 as standard output, which means standard output is now closed and reopened as the writing end of the pipe. And of course, after it, we close PFD1 because we no longer need it, since we already have standard output pointing to the writing end of the pipe. And then we simply call exec in order to execute ls. And of course, all these file descriptors, they are used, of course, they are inherited by the child process even after the exec, which means whatever ls prints to standard output will now go to the writing end of this pipe. So all the output of ls, whatever it is, with whatever system call it uses in order to print it, doesn't matter. Write, printf, who cares? All of it will go to the writing end of the pipe. And on the other hand, what does the parent do? The parent, who will be representing the word, who will be aiming to execute the word count command, must connect the standard input of this process, of the parent process, to the reading end of the pipe, so that it can read whatever the child sends to it. So it closes the writing end, since it is not interested in writing. It will not print anything to the pipe. It will not print anything to the pipe. So it is closing the writing end of the pipe on its side. It checks whether PFD0 is already equal to standard input, just in case. If that is not the case, well, in that case, it explicitly uses dup2 to make a clone of PFD0 as standard input. So PFD0 now has a clone as file descriptor 0. It checks, of course, if these calls are successful. And if it is successful, it closes PFD0 since it no longer needs it. And then it calls the word count command using exec. And of course, this word count command now, whatever it tries to read as input from standard input using scanf, fgets, gets, who cares, it will always read it from the reading end of this pipe. And of course, after it is done with everything, it closes PFD 0, we can see the parent, it closes PFD1, and of course, it waits for its two children. Okay. Waits for the children. That's fine. Okay. Any questions about this example?
What happens if the word count the second child executes before the first child?
I'm sorry. What happens when?
When the second child executes the read WC command before the first child write to the std out.
Well, in that case, if the second child, so the second child at this point who is executing word count is executed before the first child, it will try to execute the command word count. But of course, word count, in order to be successfully executed, it requires input. So word count will try to read from the standard input, which points to the reading end of the pipe, but it will not find any input there, since the other child didn't have a chance yet to execute. And what happens when you try to read from a pipe, but there is nothing to read? It blocks, and the reading command of word count will not return. So it will be frozen, it will be blocked, waiting for something to read. And it will only return when the first child gets a chance to execute and ls actually prints something, writes something to the writing end of the pipe. So we have an implicit synchronization. Yani dolaylı bir eş zamanlama var.
Okay. Thanks.
No problem. Any other questions? Okay, class. So we continue. Now, talking of synchronization, let's talk about something more serious. There are many synchronization problems that are possible between two or more processes or even threads. Now, some of them are a bit classic. Some of them are a bit relatively frequently encountered in the state of the art. One of those relatively frequently encountered synchronization problems is known as a synchronization barrier. Eş zamanlama duvarı veya engeli. What is a synchronization barrier? Now, synchronization barrier is basically when you have n processes, n being, of course, greater than 1, and you want all of these processes, basically, to reach a certain point in their calculations, all of them, before going any further. Or alternatively, you can imagine a parent process that wants to wait until all of its children have accomplished a certain task. And it will only continue after that. Now, of course, if there is a parent-child relationship between them, you can simply call wait in order to wait for all of the children to complete. But imagine that they have no parent-child relationship. Or imagine that you want all of the children to reach a certain point in their executions and not go any further before all of the children have completed it. Is it clear? Do you want me to explain it again?
Bir daha anlatırsanız iyi olabilir hocam.
Let's imagine that you have n processes and all of them are supposed to be executing a certain amount of code, a certain number of statements. Now, there is a certain point in these statements, a certain line in your project, in that file that these children processes are executing, and that is a rendezvous point. So the children execute their code, they reach the rendezvous point, and they are not supposed to go beyond that point in their course of execution before all of the other children have reached that point. We want all of the processes basically to reach a certain rendezvous point and to advance from that point only after all of them have reached it. Example, imagine that all the students in a classroom are children processes and they are solving an exam. And they are agreeing among them that nobody will deliver their exam paper to the assistant before everyone has finished. So let's say that Mr. Enis finishes his exam first. He looks around and he sees that his colleagues are still solving their exams. So does he deliver his exam paper to the assistant? No, he waits. For what? For all the other students to finish so that all of them can deliver their exam papers together. So they are organizing a rendezvous point where at the end of the exam paper, or it could be at the end of the second question. So basically you could agree among yourselves that nobody will solve question 3 before having completed questions 1 and 2. Before everyone has completed questions 1 and 2. That's a synchronization barrier. Everybody completes 1 and 2, and you continue to question 3 only after the last student has completed question 2. Is it clearer now? Yes, no?
That's clear.
So class, how can we solve this? Now, of course, if we had access to semaphores, it's very easy to solve. If we had access to mutexes and condition variables, it is also very easy to solve. But right now, we do not have access to that stuff. All we have access to is just pipes, and that's it. So can we solve this with pipes? I mean, we can also solve it with signals. That's also possible, but that is not in the scope of our lecture for now. So how do we solve this with pipes? It is very easy to solve it with pipes. So our objective is for the parent to wait for the children to reach a certain point in their executions. We are not talking about the end of the children. If we were talking about the end of the children processes, the parent could very easily just go and wait for all of them and continue only after all of the waits have returned. But no, we are talking about an intermediate point in the execution of the children. We want all of the children processes to reach that intermediate point and only continue, and the parent to continue only after all of the children have reached that rendezvous point. So what do? We solve it with pipes. Now the parent builds a pipe before creating the child processes, the children processes. Each child, of course, will inherit a file descriptor to the right end of the pipe, and it will close this descriptor once when it has completed whatever action it is supposed to complete. So it will only close the descriptor that it has inherited after reaching the rendezvous point, after reaching the barrier of synchronization. After all of the children have closed their file descriptors, well, in that case, the parent will be notified of this situation. Why? Because if it tries to read from the pipe, it will receive an end of file, in which case the parent will know that all of the children processes have reached the rendezvous point. But of course, for this to work, it is also necessary for the parent to definitely close the unused writing end of the pipe, because otherwise, even if all the children processes close the writing end, the parent process will not receive an end of file because it will still have its own writing file descriptor open. Because the only way to receive an end of file from a pipe is when all of the writing ends have been closed. Here we have an example. So we have a parent with 3 children. So child 1, 2, 3. What are they doing? Let's see. So in the main function, we declare an integer array of size 2 in order to hold the pipe. We check whether the command line arguments are correct. We set standard output to have null buffering so that it will not be buffered. So whatever we print to standard output will immediately appear on screen. So we print on screen that the parent has started, and then we call the pipe system call in order to establish the pipe in kernel memory. Okay, so now we have 2 file descriptors as pfd1 and pfd0. And then what does the parent do? Now it uses argc, so the number of command line arguments. So for example, here we have 4, 2, and 6. So we have 3 command line arguments. So it will create 3 children. So the for loop is repeated, in this case, 3 times. So for every child, what does it do? In case 0, it closes the reading end in the child. The child is then supposed to do some work. And then after a while, it sleeps a bit in order to simulate processing. So as if it is doing something very intensive. And then the child has now reached the rendezvous point. So it closes PFD1, the writing end. This means the child has reached the rendezvous point. And then it continues to do whatever it has to do. And after a while, it exits. Now, the child doesn't wait for anything else after that. It just it notifies through this closing the parent that it has reached the rendezvous point. And what does the parent do? Now, the parent, outside of this loop, it of course closes its own writing end of the pipe. It does whatever it has to do, and then it calls read on the pipe. Now, if there is at least one more child process that hasn't closed the writing end of this pipe, the parent will be blocked here, right here at this read system call. And it will only return when the last child has closed the writing end of the pipe. It will return with an end of file error. And then the parent will know that the rendezvous point has been reached by all of its children, and so it will be free to do whatever it is supposed to do. Any questions about this example?
So can you repeat, please, the parent process? Your last 3 sentences. Can you repeat again, please?
Now, the parent process is, of course, executing outside of this for loop. In the for loop, it's only the children in case 0. The parent uses default in order to loop through it. So what does the parent do? So the parent has executed the forks. The children have been created. The parent has 2 important things to do here now. One, it closes the writing end of the pipe. Why does it do it? For 2 reasons. One, because it is not interested in writing anything to the pipe. And second, if it doesn't close it, that means if you have 3 children processes, there will be 4 file descriptors pointing to the writing end of this pipe. 1 for each child process, plus this PFD1 in the parent process. That means when you call read afterwards, right here, when the parent calls read afterwards, it is waiting for what? It will be waiting, and it will be blocked at that read, waiting for the last child to close its writing file descriptor. But if the parent hasn't closed its own writing file descriptor, PFD1, it will still be waiting to read even after the last child has closed its writing end. The only way for this read to return with an end of file is if all of the writing file descriptors of this pipe of PFD have been closed. So that means the parent process must close its writing end, and all of the children processes must close their writing end for this read command, for this read system call to return with an end of file.
Thank you. So it's more clear now.
Leaving the synchronization barrier behind us, now let's talk about POPN, PICLOS, and of course FIFOs. Now with the POPN and PICLOS, there isn't really much to talk about, really. There isn't really anything new about them. It's just a method available from the C library. This is not a system call. This is a function available, these 2 functions, popen, pipeopen, and piclose. There are 2 functions available in the standard C library in order to facilitate, in order to make it easier to manipulate pipes. And what do they do exactly? Well, basically, pipeopen, popen, receives a command in a certain mode, and basically it executes this command and it connects a pipe to it. That's all it does. And returns the file stream corresponding to the pipe or null on error. So it executes the command that you give it, and it connects a pipe to the end of this command. And pclose, well, it simply closes a file stream. Now, what is the idea? Let's look at it in more detail. The pipeopen function creates a pipe and then forks a child process that executes a shell, which in turn, the shell, it means, which in turn will create a child process to execute the given command. Okay, so it is very similar to the system function. The mode argument is a string to determine whether the calling process would read from the pipe or write to it. So for instance, if you call popen with the mode being in reading, so mode is R, so the left example, what it does is the calling process on the left, it first forks and execs and creates a shell. The shell forks and execs and creates a process to execute that command. And the output of that command, so the reading end of that pipe, is connected to the calling process. So the calling process, if it tries to read from that pipe, it will read the output of that command. Or if you use the writing mode, that means the calling process, it will be able to write and send data to the command that has been executed. That's all there is to it. So nothing new with respect to the stuff that we have seen. It's just there in order to make it easier to manipulate them. So does this mean that you should be using popen and pclose? No, I do not recommend it. It is in general not recommended. Why? Because security-wise, it is very risky. Because just like system, it involves creating an instance, a process to execute a shell. And since we have no idea whether the shell of the system where your program is being executed is safe or not, popen also introduces a security risk for your process. Here, for instance, in this example, we can see popen being used with the sort command. So that means with the W mode, which means the writing end of the pipe is returned as a file pointer. So that means whatever we write to this stream using fprintf will go as input to the sort command. Basically, that's all there is to it. So all that popen does, it eliminates the need to use dup2, pipe, fork, exec, and fdopen. Any questions about pipe open? Okay, class. So now we are switching to FIFOs. Nothing really fancy at this point, as you will see. Now FIFO, a first in first out structure or a mechanism or a tool is basically just a pipe that, however, exists with a name in the file system. Now, why do we know this? I mean, why do we need this? The problem with pipes, if we didn't have FIFOs, is that they can be only used between processes that have a parent-child relationship. So pipes can be used only to communicate unidirectionally between a parent process and a child process. So what happens when you want to communicate between two processes that don't have such a relationship? Well, in that case, you can use, among other things, you can use a FIFO. A FIFO is basically just a pipe that can be used between any two processes executing on the same system. That's all. Besides that, the operational mechanisms are identical to a pipe. So it has a reading end and a writing end. It is also unidirectional. It is a serial structure. That's why they are called FIFOs. So first in, first out. So whatever you send first from the writing end appears first on the reading end. Now, how do you create a FIFO? Well, you can create it in the shell, of course, with a command and also with a system call. First, the shell. In the shell, you can create it by simply using the mkfifo command, make FIFO command. So you just call make FIFO, you give it a path for the FIFO file, and that's it. And then you have created the FIFO. Now, if you ls it, you will see that it has a size of 0, since it contains nothing. And you will see that the first letter at the output of ls is a P, denoting that this is a pipe or a FIFO. So this is not a regular file. Bu sıradan bir dosya değil. It's a pipe. But just like any other file, it has, of course, file permissions, a user that owns it, a group that owns it, time of last modification, of creation, and so on and so on. So this is the shell part. So what about the system call related to it? Now, before we go further, here we have an example of the FIFO created through the shell. So you can use the cat command in order to read from the FIFO or write to the FIFO. So if you can do it on your own time. If you create two windows, two terminal windows, where you try to read and write to the FIFO, whatever you type on one terminal will be appearing at the other terminal. Nothing fancy. It's just a file which receives input from one process and sends it as output to another process. So it can only be used for the communication of two processes, not three, only two. One for reading from the FIFO and one for writing to the FIFO. And when you're done with it, you simply remove it from the file system, just like any other file. Now, class, at this point, we'll take a break for a few minutes, for 5 minutes, and we will continue at 10 past 2. 5 dakika ara arkadaşlar. Okay, class, now we continue. And here we have the system call corresponding to the creation of a FIFO with a given path name. Two arguments. The first is the path name of the FIFO, wherever it is supposed to be created in the file system. And of course, the mode. The mode specifies the permissions for this file. So reading, writing, and executing permissions for the owner, the group, and the others. Of course, as a combination of octal numbers combined using the OR operator. Now, how do you access the FIFO? How do you write to a FIFO? How do you read from a FIFO? Well, just like an ordinary file, there is nothing fancy to it. It is just a file. So you can open it using open, or you can use the standard C library functions, fopen, fprintf, and so on. So you can manipulate it just like any other file. Example, here, for instance, you can open it using the open system call. So at a low level, open the path of the FIFO in write-only mode. So we are going to use the writing end of the FIFO. We can write whatever you want to it. And once we are done with it, we close it. And that's it. Or similarly, if you want to read from it, you just open it using either open or fopen. You can read from it using whatever you want, fscanf, fgets, whatever you like. And once you're done with it, you close it. Now, this is the important part. Now, a FIFO can have multiple readers or multiple writers. So you can have, for instance, two processes that have opened up the same FIFO file for reading. Or you can have three processes that have opened up the same FIFO for writing. Now, what happens when multiple processes write and multiple processes read from a FIFO? Now, the POSIX system guarantees that bytes from each writer will be written atomically up to a maximum size. What does it mean, written atomically up to a maximum size of, pipe boof or whatever it is, usually 4 kilobytes on Linux? This means that if you have two writers writing to the same FIFO simultaneously, a certain amount, let's say the first one is writing 10 kilobytes and the other one is writing 24 kilobytes, the 4 kilobyte pieces will be written atomically. They will be written intact, but there is no guarantee that the bytes after the first 4 kilobytes will belong to the same process. So they might be interleaved. Birbirinden bir diğerinden. Ara geçişlerle. So you can have 4 kilobytes from one process written into the into the FIFO, and then 4 kilobytes from the other process. It is possible. Not necessarily, I'm not saying that necessarily that will happen, but it is possible if you have two processes trying to write to the same file, to the same FIFO at the same time. Or maybe, just maybe, the kernel will arrange them in such a way, it will schedule them in such a way that one process will write 10 kilobytes, and then the other process will write 2 kilobytes, and it will be done. So the kernel basically gives you a guarantee up to 4 kilobytes that it will not be confused with some other writer. That's all. That's all. Another point is that in order to be able to use a FIFO, it must be opened on both ends. So at least two processes must have opened a FIFO. If only one process has opened it, for reading or writing, doesn't matter, that FIFO will block. You will not be able to read, you will not be able to write. So you need at least two processes to have opened the FIFO before they can continue. If you don't want this happening, you can use the non-block flag while opening the FIFO. Any questions? Here we have an example. So a parent that reads what its child has written to a named pipe. A named pipe is a different way of naming FIFOs. Same thing, named pipe, FIFO, same thing. So here we have a buffer size of 256 bytes. We have FIFO permissions as reading permission for the user and writing permission for the user. And we have two functions, do FIFO child and do FIFO parent. Okay, so these are for creating the FIFO, I guess. Let's see. So in the main method, so we have the parent process right now. We are checking the command line arguments. We want just the pipe name to be provided as a command line argument as pipe name. Then the parent process calls make FIFO using the name given in the command line as argv position 1, using the permissions in the constant, so reading and writing for the user. So the FIFO is created. If it wasn't able to create it, it prints an informative message. That's nice. Then it calls fork, and now we have two processes, the child and the parent. If it is the child process, it executes do FIFO child, and the parent alternatively executes the do FIFO parent function. So what are these functions doing? So the child is executing do FIFO child, and it is doing what? It receives the FIFO name as a command line argument and a certain string. What is that string? The child receives the string, this was written by the child. Okay, so what do we do with that string? So it does what? It opens the FIFO by using a nice while command, as you can see here, right at this point. Why? Because it wants to be sure that it will be able to open it and it will not be interrupted by a signal. So that is why, as long as it is interrupted by a signal, it is continuously trying to open the FIFO again and again in writing mode. So it is not taking a no for an answer. After it is opened it successfully, it is getting ready to print inside that FIFO. Now the FD has been returned as a file descriptor. It is preparing the buffer. It is printing into the buffer the message that it has received as ID string as a command line argument. It is printing it to the buffer using sn printf. It is calculating the size of that buffer, strlen, and then it prints to the standard error that it is about to write a message. And it also informs the command line of its process ID. And then it uses the repeated form of the write command, rwrite, which is just a repeated form of the write system call, in order to write to the writing end of that FIFO this message. And it checks whether it has written all of the bytes, and it just says that I am finishing. Whereas the parent, on the other hand, it symmetrically opens up the FIFO for reading. In this case, the FIFO mode is read only, as you can see it here on the beginning. And it simply reads, using a loop once again, rread, the contents of that FIFO. And whatever it reads, it prints whatever it has read to the standard error. So basically just a parent, just a child writing a message to the FIFO and a parent reading it. Any questions about this example? Now class, this brings us to the client-server model now. Sunucu istemci modeli. Now we will talk about this model a lot until the end of the semester. This is the first time now that we will encounter it. I know that you have already seen it, or you have probably at least seen it in your networking class, in your distributed systems or computer architecture classes, and so on. Now the main idea is that there are at least two systems, not necessarily distinct. I mean, they could be just processes being executed on the same system, but the general idea is that the clients, the client processes or the client systems, they are asking from the servers for a certain service. İstemciler sunuculardan belli bir hizmet talep ediyorlar. Classic examples are of course the HTTP server and a web browser. The web browser, Mozilla, Chrome, or whatever you're using, is of course the client, and the HTTP server. Can you give me an example of an HTTP server? An example of an HTTP server?
Maybe Google, Facebook, all are
Nginx.
HTTP.
Maybe Nginx.
An HTTP server program, a program that I can use as an HTTP server. Let's say I want to create an HTTP server on my computer. What do I use? What can I use?
Like Spring
Apache?
Boot.
Okay. A classic example in the Linux world is, of course, Apache. There is also Microsoft Web Server, and so on and so on. So these are just programs that you can use in order to create web servers that will run on your computer, and that will be waiting for clients to ask for a service. And of course, the clients, they will be connecting to port 80, to the HTTP port. The clients will usually be, of course, browsers, and they will be, of course, asking for web pages as a service. Now, that's the classic client-server model. Now, this is opposed, of course, to the peer-to-peer model, where there is no concept of a server and a client, and everybody's equal. So a peer is connected to a peer. Denkleriyle bağlanıyorlar. A classic example of a peer-to-peer system is, of course, the BitTorrent file sharing protocol, or clients interacting, systems interacting with a blockchain. So if I want to send some Bitcoin to Mr. Enis, he is a peer and I'm a peer. There is no server in this case. I can send directly Bitcoin to Mr. Enis. That's a peer-to-peer system. Whereas if I use a bank, that's a client-server model. The bank is the server, and me as a client, I ask the server, the bank, to send the money from my account to the bank of Mr. Enis. So that's a client-server situation. Now, having said this, there are many ways of implementing client-server models, and there are many flavors. Farklı türleri de var bu meretlerin. Flavors depending on the number of servers. Sometimes you always have just one server. Sometimes you can have multiple servers. Sometimes you have a limit on the number of clients. Sometimes there is a restriction on the type of the communication that you can have between clients and servers. So is it a simple request or a request reply situation? Or the way of handling the clients. So some servers handle the clients one by one. Other servers handle the clients concurrently at the same time, and so on. Now, of course, in order to implement a client-server model, you need a solid communication infrastructure. You need to be able to communicate reliably between the clients and the servers. Now, of course, at this point, we are not going to use sockets because we haven't seen sockets yet. But in order to show you the power of FIFOs, we are going to look at an implementation of a client-server model using only FIFOs in order to achieve it. Now, since we are using FIFOs, this means that the server, as well as all of the clients, they must be executed on the same system. Hepsinin aynı sistemde çalışıyor olması lazım ki FIFO işe yarayabilsin diye. As a side note, parantez olarak geçelim. In the Windows world, a FIFO can be established between processes running on different systems. But that is specific to the Windows world. We are not going to talk about that. Now, what is the task? What is the service provided by the server? It's very simple. The server's job is to provide unique sequential numbers to the clients that request them. So that's the service that we are providing, not web pages, not anything else, not songs, not movies. No, the server, when a client is connected to it, it simply sends a unique sequential integer number. Okay, that's the job of the server. It can be simple, it can be complicated, it doesn't matter. So how are we going to achieve this with a FIFO? Now, the first impulse is usually to create a FIFO between the server and the clients. So there will be a FIFO, the clients will write their request, and the server will respond with that request. But this is, of course, a very bad idea. Why is the bad idea? Because if you have one server and you have multiple clients, in that case, the multiple clients will all of them try to read the response of the server from the FIFO, but very probably they will read each other's messages. So this whole thing will fail. I will make a request as a client, Mr. Enis will make a request as a client, the server will respond to me, but maybe Mr. Enis will read the response of the server. So he will read the response that I was supposed to receive. So that is why this thing doesn't work with just one FIFO. Therefore, so what do we do instead? Each client can create a unique FIFO. Each client can create a unique FIFO that the server can use in order to deliver the response to that client. But of course, the server needs to know how to find each client's FIFO. So if two clients connect to me as a server, they need to first tell me which FIFO they are going to use so that I can communicate with them using that FIFO. So first the client contacts the server, giving him some information about himself or herself so that we can create a FIFO specific to that client. And then the server makes his calculations and uses that client-specific FIFO in order to respond to the client. And how can it be client-specific? Well, since we are all running on the same machine, we can simply include the process ID of the client in the name of the FIFO, which leads to this kind of a structure. So here we can see client A and client B with, of course, different process IDs. They use the same server FIFO. There is only one server FIFO in order to make their request. In their request, they write their process ID. So 6514 for client A and 6523 for client B, which means the server now knows the name of the FIFO that it is supposed to use in order to respond to client A and in order to respond to client B. So it makes its calculations, it writes its response to the corresponding client FIFOs, and that's it. Now, this means, of course, you will need a new FIFO every time that the client connects to the server. Any questions about the organization? Another practical issue. So let's say that we have taken care of this part. Now, another practical issue is how to organize the data in pipes and FIFOs, because it is a byte stream. So if you send just one message, well, that's easy. You just send your message, the other side reads it, and you're done. But what if you send multiple messages through the same FIFO? How will the other side know when one message ends and the other message begins? Now, in order to solve this problem, there are many ways of approaching it. The three classic approaches is one, to use a delimiter character. So you use a special character in order to denote the end of each message. Option two, you have a header which tells beforehand, before the message, how long it is, so that the other side will know how many bytes to read in order to reach the end of the message. Or three, all your messages can have the same size. So it is always n bytes. So the other side knows exactly how many bytes to read. These are the three most classic options when it comes to denoting the end of messages. So now let's look at the source code. And it's a simple example of a server and multiple clients, a server-client model that communicate on the same system by using one server FIFO and multiple client FIFOs. So here we can see that the server FIFO is in the temporary directory, sequential number SV. The client FIFO template, so it will always be in the temporary directory with a sequential number client dot and a certain integer. This integer will be the process ID of the client. And of course, the length of the client's FIFO name, which is quite long. It's a generous allowance. So here we have the struct, which is representing a request by the client. It simply contains the process ID and, of course, the length of the desired sequence. And, of course, struct response, which simply represents the response of the server to the client. Now, what does the server do? Now, this is an iterative server. What does it mean to be iterative? It means that it responds to one client and then it responds to the next client. It doesn't do anything concurrently. Eş zamanlı işlem yapmıyor. Birine yanıt veriyor, işi bitince sonrakine yanıt veriyor. So it will create the FIFO. It must, of course, be run before the clients. The opening of the FIFO, of course, will block until the clients open it as well. Remember, a FIFO always blocks until both ends are open, or at least two different processes have opened it. And the second open ensures that the server doesn't see an end of file if all the clients close the right end of the FIFO. So it will at least have one open file descriptor so that the end of file will not be received by the server who is trying to read the requests. SIGPipe is a signal that occurs when writing without a reader, and by default it kills. So that's why you must take a precaution to ignore it so that the server will not be killed just because there are no clients. So let's look at the server. So here we have the initial variables, server FD, dummy FD for the file descriptors. We have an array client FIFO representing the array which will contain the name of the client FIFO. We have the structs for the request and the response, and sequential numbers, they start from 0. It is just a service for the sake of it. So UMask is set to 0, so that we will have the permissions that we want. We call mkFIFO to the already predefined path with reading, writing permissions for the user and writing permissions for the group. So the FIFO is created. The server opens the server FIFO in read-only mode, and it waits. Now, at this point, of course, it will be blocked until at least a client has opened it as well. Now, once it has been opened, the server at this point opens once again the server FIFO, so that even if the clients close it, it will not receive a SIGPipe error. And not only that, but it also sets to ignore the SIGPipe signal. Now here, this example is a bit old and it is using the signal system call, but remember what I told you, never use the signal system call and instead use SIGAction. And then in an infinite for loop, it waits for requests to arrive from the clients. So it tries to read the server file descriptor, the reading end of the FIFO. And if there is nobody writing, it will be blocked at this point. So if some client has written something, this read system call will return. It will read the request into the rec structure. And then what does it do? It prepares at this point the response for the client. It writes up some sequential number into the response struct. It writes it to the client FIFO, whose name has just been prepared here using the smprintf. So we have already read the process ID, and we have the process ID of the client, and we have written it right here at this point into the buffer containing the name of the FIFO that we will use in order to communicate with the client. We have opened up the client FIFO, we have written the response right here, and then we close the client FIFO's file descriptor and update the sequence number so that we'll be ready to respond to the next client. On the side of the client, on the other hand, we have the global variable to hold the client FIFO name. We have a method remove FIFO in order to delete the client FIFO from the system. And what does it do? Well, it simply receives the, what does it receive? Here we see in the example, it receives 3 and 2, etc. So I'm guessing these are, where is argv1? Here is argv1. So we are receiving the identities of the clients, I guess. And it prepares, of course, the buffer that will contain the name of the client FIFO. It creates with mkFIFO the client FIFO. It uses the addExit system call in order to register the remove FIFO method, which will be executed when the client exits. And so that means when the client exits, the client FIFO file will be removed from the file system. It prepares the request struct by including its process ID in the PID field, and the sequence length provided as a command line argument is included in the sequence len field of the struct. It opens the well-known server FIFO in write-only mode. It writes the request, and then it opens up the client FIFO and waits with read for the response of the server. And once it has received the response, it prints it on standard output and exits successfully. Questions, class?
Apache de aslında bunu arka planda aynısını yapıyor değil mi hocam? Bu işi yapıyor yani.
Questions, Mr. Enis?
Apache'de arkada bu işi yapıyor değil mi aslında?
So what is your question, Mr. Enes? In English? Come on, Mr. Enes, you can ask the question in English. You can do this.
Devam edersen. Sen benim eski halime dönersin. Eski halim. Böyle gidecek.
Come on, class, you can ask your questions in English, no problem. No questions? Should I assume that everything is understood?
Can we say, I have a question actually.
Yes.
Can we say that pipes are faster to operate than FIFOs? Because pipes operates on memory level and FIFOs we need to create a file and retrieve the data from the file.
Will it really make that much of a difference? I'm not sure at this point, because I don't think that it will actually go to the hard drive. So so do not think of it at this point as that you are writing the data, it goes all the way to the hard drive, and then it gets back from the hard drive for the other process to read it. There is an intermediate mechanism behind the FIFO, which is called file mapping. So even in the case of a named pipe, so even in the case of MK FIFO, you're actually still dealing everything in memory. So that is why I do not expect for any significant performance changes between the pipes and named pipes. Do not be fooled by the fact that a named pipe is represented as a file in the file system. This doesn't necessarily mean that every time that you write something, it has to go all the way to the hard drive to be stored in the file system. And then when you try to read from it, you actually have to go to the hard drive to retrieve it. Because remember, the kernel has a very efficient buffering system. So it will only actually write it there maybe if you actually flush it and tell it to actually keep it there on the hard drive. But in general, in practice, since you will be writing small amounts of data and not gigabytes to a named pipe, very, very often, everything will be taken care of in the buffer of the kernel. So in practice, it won't really make that much of a difference. The only advantage of FIFOs with respect to the named pipes is that they allow you to establish a communication channel between processes that are not necessarily related. That's the main advantage of FIFOs. Otherwise, you will be restricted with communicating only between processes that have a parent-child relationship. Now, is this the paradigm that is used in client-server models? Of course not. They are not using FIFOs because clients are usually located in different machines. I mean, I am using my machine in order to connect to the web server of our school, which is another machine. And I cannot use a FIFO in order to establish that communication. I have only one option, and that option is to use a socket. So if you are connecting to a server using your browser, you are using a socket because that is the only tool available in order to establish a channel of communication between processes located on different machines in the POSIX world. In Windows, you have multiple options. So this is just an educational example. This is not how, this is not the type of communication that is used between clients and servers, not FIFOs. 99% of cases, they are using sockets. We will talk about sockets towards the end of the semester. Now, class, this was the end of the 6th lecture. and I'm a bit indecisive about whether we should have our midterm next week or whether we should continue with one more lecture before the midterm. I haven't decided yet, so I will make that decision today.